Okay, welcome back, AP Chemistry students, to topic 4.3, representations of reactions with particulate drawings. We've done particulate drawings in the past in Unit 1 when we were doing stuff with moles and mole amounts, but now we're going to use particulate drawings to do stoichiometry and represent reactions. So here's a little bit of a review of particulate drawings. We're going to let a white triangle represent oxygen and a black circle represent carbon. And in this question here, it says draw 4 moles of carbon dioxide, or 4 CO2 molecules. Okay. So to draw 1 CO2 molecule, we're going to need a black circle to represent carbon. And then attached to that black circle, we're going to need 2 triangles to represent the oxygens, and those triangles should be white. Okay. So there's 1 molecule, or 1 mole, of CO2 drawn out with a particulate drawing. However, it asks for 4, so we need to draw 3 more. Alright, so there are 4 moles of CO2 drawn out with particulate representation. These symbols over here could be anything, but the exam or the question will let you know what symbols you should use. Okay, and you are typically at liberty to attach them in any order you want down here, but because you should be familiar with the Lewis structure of CO2, which looks like this, you'll note that the carbon is central. Okay, now let's try H2O, a little review of that one. Wants to do 2 molecules of H2O and let a white circle represent hydrogen and a black circle represent oxygen. Okay, so to do 1 mole, we're going to need 1 black circle to represent the oxygen, and then attached to that black circle we need 2 hydrogens, or 2 white circles to be hydrogen. And it said to do 2 molecules of this, so we'll do 1 more, and just for giggles we'll do it upside down. Doesn't matter the orientation, just as long as you draw it correctly. Alright, so there's a quick review of particulate drawings. Now let's move into using particulate drawings to represent reactions. Okay? So here's a very classic reaction: 2 molecules of H2 reacting with 1 molecule of O2 to form 2 molecules of H2O. All right, and up top they were really nice and gave us a key of what each one should look like. Okay, usually they don't do that. Usually they just give you this. Okay, so for H2, we know it's going to be 2 white circles next to each other. Okay. They did 2 white circles next to each other because it's saying that there are these 2 hydrogens are attached by that subscript 2 there. Okay, it would be incorrect to draw 2 separate hydrogens like this, because this would be equal to 2 single H's. So you do need to be careful. Right, and this asked for 2 moles of the double H2, or the diatomic H2. And then over here it says we need 1 mole of the O2, so I need to draw 2 attached black circles because it's subscripted 2 here. Again, it would be incorrect to do 2 separate black circles like this, because this is saying that this is 2 single oxygens, and that's not what you want. You want something that is a O2 molecule. And we already know what H2O looks like, and it says we need to draw 2 of them. So you should be noticing that the coefficients out in front dictate how many of each drawing you should make. And the coefficients are molar amounts, ladies and gents. 2 moles of hydrogen reacting with 1 mole of oxygen will make 2 moles of H2O. Alright, let's try this one. 2 moles of Na reacting with 1 mole of Cl2 to make 2 moles of NaCl. To do 2 moles of Na, should I do 2 attached squares like this, since the square is represented by Na? If you said no, then you are correct. That would be wrong, because this right here is equal to Na subscript 2, two NAs attached to each other. That's not what this asked for. This is a single Na here, and we just need two of them. Two single NAs. Okay? Two single sodiums. For Cl2, it says that one chlorine is represented by a single triangle. So in this case, would it be okay to do two separate triangles? No, it wouldn't, because this is equal to two single Cls. The question said Cl2, so we would need to draw those two triangles attached to each other. So I'm going to draw them attached like this, one below the other, kind of looking like a little bow tie. You could have drawn them attached with them both facing upward if you wanted to. I don't care, just as long as you show them attached. All right. And this is going to make, two formula units of NaCl. And it gave us the look for NaCl right there. There's 1 mole of NaCl. And then 2 moles of NaCl. So by now you should feel comfortable with drawing particulate models or doing particulate drawings, because we've done it in the past. You basically just need to follow the directions or follow what the reaction is saying. Now let's get into using particulate drawings or stoichiometry. Now this is where it's going to get a little difficult, okay? Let's take this reaction right here, where 2 moles of sodium monoxide is going to react with 1 mole, again there's an imaginary 1 there, with O2 to make 2 moles of sulfur dioxide, okay? And it told us down here that the sulfur is represented by an open circle or a large white circle, and then a smaller black circle will represent the oxygen, okay? So SO is 1 S and 1 O, which means this must be the SO molecule here because it's got 1 white circle for the S and then 1 black circle for the O. And it says for every 2 of these, we'll react with 1 of these. Okay, so let's see if I can knock out 2 of them down here. There's 1, 2 of the SOs reacting with every 1 mole of the O2, and the O2 is represented by those 2 black circles there. Okay, so I've been able to point out from this reaction here 2 SOs and 1 O2. And when I can pull those out, I will make 2 SO2 molecules. So over here on the product side, let me have a white circle represent the S, and 2 black circles represent the O's for SO2. And it says I can make 2 of them for every 2 of these, and 1 of those I knock out. So I'll put another one here. And then we've just predicted the products that this reaction can make. Let's go back and see if we can make any more though. Okay, did we use everything that we could? Alright, let's see if I can knock out another 2 SOs. Yes, I can. Alrighty. And can I knock out another 1 O2? I sure can. Right there. So that means I can draw another 2 SO2s now, based on the reaction above. So I can make 2 of them. For every 2 of these, and 1 of those I knock out. Alrighty, let's see if we can make any more. 1, 2, and then 1 of those. So that means I'll make another 2 of these here, based on the reaction above. Okay, let's go back. Can I make any more? And if you say, no, I can't make any more, you are correct. Because look, I have run out of SOs. Okay, I have no more sulfur monoxide. I do have an extra oxygen lying around, or an extra O2, but there's no more SO around to react it with. So I cannot make anything else from this reaction. Okay? So, what do we call the reactant that runs out first, and then what do we call the reactant that runs out, that doesn't run out, that has leftovers? Well, the reactant that runs out first, which in this case was the SO, we call that the limiting reagent. Because it ran out first, it limits us to how much of the molecule or how much of the products we can make. As you can clearly see, we ran out of SO first. No more left. Which reactant had leftovers? Well, that's going to be the O2 because we had some of that left over at the end of the reaction. So it will remain there unreacted because there's no more SO left to make any more products here. And we were able to make a total of 2, 4, 6 moles of product given all of that reactant that we had over here. Alright, let's try another one, okay? This case we have CH4 reacting with 2 O2 to make CO2 and 2 H2O molecules, okay? So it's a little bit more of a complicated reaction, but the process is still the same, okay? And we just need to follow the reaction as it is. We have a black square representing carbon, a white circle representing hydrogen, and 2 black circles representing oxygen, okay? So based on this reaction, for every one of these, I need to be able to knock out 2 of the O2s, and it looks like I can. And when I do that, I can make 1 CO2. So to do CO2, I'm going to do a black square. And CO2 has 2 oxygens in it. So we just need to do 2 black circles attached to it. And then there you go. You have 1 mole of that, but I can also make from this reaction 2 hydrogen or 2 water molecules, so we'll do 2 water molecules as well. Okay. Alright, let's see if we can make any more. Alright, I can knock out 1 of these and 2 more of these, and as a result of that I can make another CO2 molecule. Because that comes from there, but I can also make 2 more H2O molecules, so I should draw those over here as well. And then if we go back and look, it clearly shows that I cannot make any more products because I've run out of CH4s, which would be my limiting reagent, and then I had plenty of oxygen left over. So that's my excess reagent. Okay, now let's see if you can think backwards. Alright, ladies and gents. Same idea, except we're going to be going from the products over to the reactants, okay? So according to this reaction right here, for every 2 molecules of H2O2, which is hydrogen peroxide, that breaks down, it makes 2 moles of water and 1 mole of O2. Okay, so let's just work backwards. For every 2 of these I knock out, I should be able to knock out 1 of those and make 2 of these things over here. So let's do that. 2 water molecules for every 1 oxygen should make 2 H2O2 molecules. So here is and the oxygen is represented by a black circle. White is the hydrogen. So here is how I'm going to draw the H2O2 molecule. Right. You can draw it any way you want, just as long as you have the correct things in there. And it says I can make 2 of them for every one of those I knock out. So I'm going to make another one here. Perfect. Let's go back and see if we can knock any more out. For every 2 H2Os and 1 O2, I should be able to make 2 of the product, okay? And I surely can. So that over there, ladies and gents, that's just the gist of doing particulate drawings in stoichiometry. You need to follow the coefficients of the reactions and see what you can knock out in order to make products, or if you're thinking backwards, in order to make the reactants. Please rewind this video and go over it one more time so that you can see these examples multiple times before you work through the Nearpod activity. Alright, take care and we'll see you in the next video.